ആശ്രിതർ ഞങ്ങളുടെ അന്ധതയെല്ലാം മാറ്റേണമേ. അദ്വൈതാക്കളാം ആശ്രിതർ ഞങ്ങളുടെ അന്ധതയെല്ലാം മാറ്റേണമേ. പരമാണുവിലും കുടികൊള്ളും ദൈവമേ, പാവനരൂപ പരമ്പൊരുളേ.
Thank you. Now I invite Dr. Archana Pedas, Associate Professor and Head, Department of Science and Humanities, to deliver the welcome address and to briefly mention the objectives of conducting this FDP.
Respected Chief Guest Dr. T.P.D. Rajan, Senior Principal Scientist, Material Science and Technology Division, CSIR National Institute for Interdisciplinary Science and Technology, Trivandrum, Principal Dr. S. Vishwanatha Rao, Director Father John Verghese, Deans and HODs, participants from various colleges, and my dear colleagues. It is indeed a great pleasure to welcome all of you to this 5-day International FDP on Engineering Next Generation Materials organized by the Science and Humanities Department of MBCT. The purpose of conducting a 5-day FDP is to provide the participants an opportunity to deepen their understanding of cutting-edge material science and engineering concepts, including advanced material synthesis, characterization techniques, and applications. By staying updated on the latest developments in material science, faculty members can enhance their research capabilities and contribute to the advancement of knowledge in their respective fields. This FDP will aid in the development of new courses and the integration of advanced material topics into the existing curricula, ensuring that students are exposed to relevant and current knowledge. This 5-day FDP focuses on developing next generation materials, which are crucial for advancing various fields of engineering and technology. By exploring emerging materials and technologies, faculty members may identify opportunities for innovation and entrepreneurship. This FDP can guide in translating research findings into commercial opportunities or startup ventures. Our chief guest of the day is Dr. T.P.D. Rajan, Senior Principal Scientist, Material Science and Technology Division, CSIR, National Institute for Interdisciplinary Science and Technology, Trivandrum. His main area of research is on development of metal ceramic composites, functionally graded materials, surface treatments and coatings, nanocomposites, light alloys, and development of engineering components and structures using metal ceramic composites and light alloys for various fields such as automotive, aerospace, defense, nuclear, and general engineering sectors. Since 2002, he is actively involved in the research and development of various processes and materials of metal ceramic composites, mainly based on aluminum alloys reinforced with particulates of silicon carbide, graphite, boron carbide, fly ash, and alumina, and short fibers of carbon and aluminosilicate. He has developed various engineering components such as functionally graded brake rotor disc, cylinder liners, pistons and gears for automotive applications, composite armors, gear housing, and piston rings for battle tanks using aluminum matrix composites. Currently, he is engaged in development of ultra-fine grain aluminum composites for aerospace structures. He has published about 145 technical papers and filed 2 patents, guided 12 PhDs, 35 MTech, 4 BTech, and 8 MSc theses, and currently guiding 7 PhD students. He is also the recipient of various national level awards such as IIM NALCO Gold Medal, IIF Research Award, INA Innovation Award, and SOLI Commiserate Award. We are indeed privileged to have such a distinguished personality as our chief guest today. On behalf of Baselios College of Engineering and Technology, I welcome Dr. T.P.D. Rajan to this function. Our principal, Dr. S. Vishwanatha Rao, was a source of encouragement and wholehearted support right from the day we started planning for the FDP. His valuable suggestions and timely inputs helped us in turning this FDP into a reality. On behalf of the Department of Science and Humanities, I welcome you, sir. Our director, Father John Verghese, is a constant source of motivation for all of us. His valuable comments encouraged us to think one step ahead than what we had actually planned for. On behalf of the Department of Science and Humanities, I welcome Father John Verghese to this inaugural function. I would like to extend a very warm welcome to the coordinators of this FDP, Dr. Preeti PC and Dr. Ranjini M. Nair. Their effort and enthusiasm put forward by both of them was amazing. They had taken care of even minute details and were very meticulous in their planning. I extend a very hearty welcome to all the participants who have joined us or who will be joining us, both online and offline mode. Last but not the least, a very warm welcome to all the MBCT family members who are gathered here for this inaugural function. Thank you.
Thank you, ma'am. I would like to invite our Honorable Principal, Dr. S. Viswanatha Rao, whose vision drives our institution forward for the presidential address.
Chief guest of the day, Dr. TPD Rajan sir, Director Father John Verghese, Deans, HODs, and my faculty colleagues. Good morning to all of you. When I look at the topic, it is very clear that this topic cuts across all the engineering disciplines. So it is something very important for all of us to consider, being faculty of the various engineering disciplines. We have computer science, electronics and communication, electrical and electronics engineering, mechanical engineering, as well as civil engineering. So as faculty of these departments, I think we have a number of very relevant topics that are being lined up in this FDP. Now, if we look at the innovations in material science, this could be basically driven by two major aspects. One is by the regulations formed by the government. The other one is based on the need of the applications. Now we know there is substantial amount of waste or garbage generated when we use materials in the form of different products. And because of this, government has implemented a lot of environmental regulations. And in order to comply to these regulations, innovations have been, triggered by the research community. And we have seen that a number of new materials or products have emerged based on this. And this is something which we are looking at when we talk about sustainability. Okay, a lot of terms emerge as we move on. We hear about sustainable engineering or sustainable materials. We talk about recyclability. So there has been a lot of re-evaluation happening in the field of recyclability. And that is where again the terminologies such as circular systems have emerged. And then it leads on to circular economy, where everything we try to make use of them, reuse of them, and from starting to end, the cycle continues so that we don't have something kept aside as a garbage. Now, another aspect or another area that is happening is with respect to smart materials. Smart materials are something very important, which are evolving based on the industry demands. There also we see materials looking at the advanced concepts, and a lot of startups who are focusing on new approaches. We even talk about self-healing materials. One of the issues when we look at the materials which we are using in the applications which are exposed to the environment, sunlight or rain or even the heat, we always find degradation in the materials. That is where the concepts of self-healing comes into. And also there are materials which are evolving where some kind of intelligence is being built into. Okay, where you can have materials which can be supported with programmability. And in the modern era, we talk about material informatics. Okay, this is again, if you look at, there are many opportunities, many areas evolving, where the advantage of emerging technologies like programmability, data mining, or deep learning, artificial intelligence, these are being made use of in order to, bring in more effect into the innovations with related to the materials. Of course, there are other areas where we talk about nano materials. One of the objectives is always to miniaturize the devices that we use. They have their own advantages, so that more information or more content can be put into the same size when we start miniaturizing. You can look into the mobile phone, for example. The size of the mobile phone which was there in the earlier years, compared to that, even the sizes have become small, and you can see the content that has gone into that. So these are all again innovations that have happened in the material science area, which have been brought into engineering, which have been brought into the technological aspects. Again, if you see, there is something related to advanced composites, where I know sir is an expert. You will be able to hear more from that. This is where a lot of experiments are going on in terms of identifying new material composites which can provide more strength, more efficiency, which can be giving more durability. Okay. And of course, the weight get reduced. When the weight get reduced, there are many other advantages. If you can retain the strength and durability, it becomes more efficient, more energy, saving, and many other advantages come into force. So if you look into, we can go on and on into these different kind of evolutions happening in the area of material science, which are becoming more and more beneficial to the requirements as we progress the technology. And I hope this FDP will be extremely useful for the entire engineering community. And I request all of you to make full use of it, so that, as mentioned in the welcome address by Archana Miss, you can always use that knowledge to advance your research activities, as well as bring in some of these aspects into the curriculum for the benefit of the students. So I wish you all a very enriching experience during these 5 days of the FDP session. I thank you all for being part of this, and once again thank our chief guest, Dr. TPD Rajan, for joining us for this inauguration, as well as for providing one of the talks in the session, maybe the first session. We thank you, sir, for your valuable time. Right. Thank you all.
Thank you, sir. It is now time to introduce our esteemed chief guest for today. We are honored to have with us Dr. TPD Rajan, who has graciously accepted our invitation. He is a senior principal scientist in the Material Science and Technology Division, CSIR, National Institute for Interdisciplinary Science and Technology, Trivandrum. I now invite Dr. TPD Rajan for the inaugural address.
Very good morning to all. Respected Principal of the College, Dr. Vishnadha Rao sir, beloved Director of the Institute, Father John Varghese sir, Head of the Department Science and Humanities, Dr. Archana Madam, and all dear faculties and the participants through online. I am extremely grateful to the management of Baselios College of Engineering and Technology for inviting me to inaugurate this international faculty development program on engineering next generation materials, and also to give the first lecture on advanced metal matrix composites for structural and functional application. As mentioned in the presidential address by Dr. Vishwas sir, that materials play a role cutting across all the disciplines of science and engineering, and even medicine too. And if you tell that materials is a boundary-less subject where all the people utilize it, if you want to realize any technologies, just you take in and around whatever you see is either an organic or inorganic materials. And we as a scientist used to tell that even our body is an organic composite with reinforcement of inorganic materials. That means you have a bone with full structure of calcium hydroxyapatite, and which is been as a basic structure, which really gives the mechanical strength to their body. And you have the all organic medium in and around it, which creates a lot of functions. And even if you take interior of your bone structure itself, it forms a functionally graded structure where the outer structure of the bone gives the real strength, and interior of the bone generates a lot of body fluids and everything. So you can, so even nature, mother nature has created very wonderful materials, and we are even exploring the what is available in nature, and we are still hunting towards engineering new materials. And as technology develops in different disciplines, we need more and more new materials to realize the technology, utilize its function. Maybe whichever the discipline may be, electronics, communication, aerospace, automotive, medicine, everywhere you need. Even the medical field, you want to have a compatible materials which can fit into the body, but it can either it acts as a implant to your body and so on. Same, for example, it is the titanium material. Same material finds another application in the aerospace. For example, titanium alloy, titanium 6 aluminum 4 vanadium is a very versatile alloy which is being used as a implant in the body, as well as it is being used in the rockets for the launch vehicles, in the satellites, in the missiles, and so on. Similarly, you take that after the invention of aluminum, because I am in the area of aluminum, just I will tell how the engineering of aluminum finds versatile application in different fields. So you know that aluminum by 2025 we are reaching 200 years of its invention. So it is invented in 1825, and initially people used to tell that the kings has eaten in aluminum plates and the subordinates has eaten in silver plates. That much costly was there when the aluminum was invented. But later the technology of extraction has improved. The electrolysis technique, the cost of the aluminum has come down, and it has found wide application, starting from the utensils in our kitchen to the launch vehicles which is being put in the space, satellite in space, or the missiles, or even the electrical wires which brings power to this room from the where it is being generated. And how these things happened actually, because we know that the aluminum is in the nature is in the form of bauxite, and this bauxite is converted to alumina. Then this alumina is converted to aluminium. Then once pure aluminium comes, it cannot be used as such. Then either we have to do an alloy or we have to form a composite. That's how the engineering of materials or the engineering of alloys comes. And if you want to keep on improving its properties and functions, either for structures, just like it can be put in aluminum frames or the launch vehicles, or as a functional materials for conducting electricity, or to as a heat sink to conduct the heat which is generated in a lot of avionics and electronic systems. Whatever, even the computers and other things, if you see backside, you have a heat sinks which extracts the heat from the processor and it dissipates out. There, the thermal conductivity of aluminum is taken care. And if you want to have the electrical wires, the electron mobility is taken care. And if you are put in the launch vehicles, the strength is more important. So accordingly, we have to design the alloys. Maybe, for example, you know that in rockets and all, the why aluminum is used. We have a steel which is having higher strength, but the lightweight comes because their density matters. The density of aluminum is around 2.7 gram per cc, and the iron is around 7, which is almost close to triple that of, or the copper means it is almost triple. And even though we know that copper has better electrical conductivity, but we are not using for electrical purpose for two reasons. One is the cost, and second is the heavy weight. So we cannot have the copper wires throughout all the network. So what they thought is the next better electrical conducting material is aluminum, but aluminum as such you cannot use it because it creeps. So they started alloying with minor alloying addition to the aluminum, and then they started using in the electrical wires. And these wires, the problem is again after sometimes it get creeped, and it's come down. So they started to put inside a core, then wind with an aluminum. So you have to have a high strength of the material as well as high electrical conductivity. So the first place where they started using this aluminum is either for utensils. Apart from that, they gone for this electrical systems. And in the case of launch vehicles, airplanes, and if you see the almost the initial airplanes, almost 50 to 60% of structures are made of aluminum, because this has come because of the mainly the lightweight, because you have to have a heavy steel has been replaced with, and even now the automobile structures also being replaced with aluminum materials. So they started developing new types of alloys. So they started initially the cast alloys, which has a ultimate tensile strength of maybe 200 and 250 megapascal. Then they have gone for the 2000 series of adding copper or adding magnesium, adding nickel into that, and they developed the 2000 series, which goes around strength to 400 to 450. So to keep on increasing strength, then they gone for aluminum zinc-based alloy 7000 series, and they started using in the aircraft structures. But each systems has their own limitations and difficulties, because aluminum 7000 series has difficulty in the corrosion because its corrosion property is not good. So then they designed the other corrosion inhibitors and the materials which can protect aluminum. Anodizing is the best way, but still they go for other types of materials. So you can see how for an application of a single aluminum to different structures, how the engineering takes place, or the engineering of the alloys takes place. And even the aluminum is, we are working in a project with our light compact aircraft. And again, this light compact aircraft, the fuselage structures mainly consist of the aluminum, and over that they use this composite panels. And here, this aluminum, they use normally the 2000 series. Now, the problem is the 2000 series, the weldability is not good. So they've gone for a newer alloying element where we add minimum amount of scandium into that. And one of the problem with the scandium is the availability of scandium. I don't know, scandium is one of the costliest metal, just like gold and platinum. Per kg of scandium is close to 10 lakhs. So you can see the cost of it. But it is added in a 0.2% of into the aluminum, and whatever it remarkably changes its property. That is how the new engineering alloys are being made, and this have better weldability. So that means instead of scooping out the material, they can directly weld. They can use it. The density is better than that of the 2000 series and so on. And now currently the many of the countries, Russia and other people have started using, and we are working on this material with Hindalco Aluminium Company. And actually, I was just telling to Krishnavan sir, day after tomorrow we are visiting Mumbai for the development and the industrial trial studies of this material. So this is one application. Another application of aluminium is that you know that aluminium has very good thermal conductivity. I think next to silver and copper, aluminium has very good. That means the heat dissipation property is good. But the problem is when you go for an electronic systems, the heat dissipation property alone is not enough. The problem with the aluminum is the expansion of the aluminum is 23 ppm per degree C. That means if you have any electronic systems over that, and the because of the larger expansion, the contacts between the electronics in the PCBs can get detached, and it can create problems. So then they thought that we have to engineer new materials which can have low CT and high thermal conductivity. So low CT means low coefficient of thermal expansion. We have to use composite. I think during my lecture I will give the details of that. What we have done is that we had started incorporating silicon carbide, diamond, graphite, graphene, and many of these materials, so that the CT can be brought below 10 ppm per degree C. So we have the thermal conductivity of aluminum, pure aluminum is 230 watts per meter Kelvin. But to have a structural dignity, we go for alloying, and we make a 6063 alloy with aluminum, magnesium, and silicon. And this has a thermal conductivity of 200 to 210 watts per meter Kelvin. But even this alloy cannot be used in electronic systems. So then we have to go back to composite making by just infiltrating with silicon carbide into the aluminum or with the diamond particles. Even there is a wonder. We can tailor or engineer the material to whatever requirement we want. If you add silicon carbide, we will get a CT below 10 ppm per degree C, and we'll get a thermal conductivity 180 to 200 watts per meter Kelvin. But if you want to have very high thermal conductivity, we can incorporate metal bonded diamonds or synthetic diamonds. We can go 500 to 600 watts per meter Kelvin. That is tripling the total thermal conductivity. But the cost will go high, the machinability go high. So every time when you improve the properties or modify the alloys, so there are some advantages we get and some disadvantages we get. So what we had done, we made this aluminum silicon carbide composite we had used, because because all fighter aircrafts have this digital flight control computers which control the flight and which communicates with the ground station and even the radar systems identifying the other fighter aircrafts and so on. So there are a lot of heat is generated. The problem with this is that we cannot have a low thermal conducting material. So they keep a central plate, which is a heat sink, which is made of this aluminum, and there will be two PCBs at both sides. And each fighter aircraft has 4 PCB boards, and which controls. Actually, one is the main operating system, and there will be 3 dummy systems. So this particular digital flight control computers is very recently indigenized by our Bharat Electronics Limited. But the problem with that is still almost 60% of the material which is used for this light compact aircraft is being imported from either USA or UK and so on. So maybe 2 years back, what has happened is that US has one of the company has started supplying. So they were hunting for new people whom we can. That's how we ventured into this development of aluminum silicon carbide composites. So now which can provide 210 watts per meter Kelvin with the low CT of around 9.5 and so on. And now we had put into the testing operation. And once the flight that is ground testing is over, we have to go for airworthiness certificate. Once the airworthiness certificate is done, then it can directly replace the imported material we used. That's how we are working a lot of program on aerospace and other systems. And typical another example is there, most of our even launch vehicles, especially with VSSA and other people's, a lot of aluminum components are used in the liquid engine, liquid inlet pipes and so on. And mostly in the earlier days, what they had done is that they had taken the technologies from either Russia or France, and we try to indigenize our own selves. Then we have to design the alloy, we have to develop the what is a suitable alloy for the particular component, then make the component, and once it is qualified, then we'll be handing over to Hindustan Aeronautics Limited for continuously producing the materials. So now you can see a simple aluminum, how it has been used for diversified application. So it's not only even for neutron shielding. Once you embed boron carbide is well-known neutron shielding materials. Once you put inside, we can use it and make a casket which can transport the spent nuclear fuel from one place, or the nuclear fuels from the reactors or the mineral processing plant to the reactor site and so on. So they make this. So aluminum in a different forms find different place, and it was only possible because of engineering this material of pure metal aluminum into different forms, I think. So I think with this I will cut short my introductory inaugural lecture. I think I was able to give a glimpse that how engineering new materials and new alloys will be useful for wide different disciplines of science and technology. So thank you very much for the invitation, and I am glad to deliver this inaugural lecture and declare this FDP program inaugurated. Thank you very much. Thank you.
Thank you, sir, for an informative speech. I'd like to invite our director, Reverend Father John Vargas, for the felicitation.
Good morning to one and all. The guest of honor, Dr. TPD Rajan, Senior Principal Scientist, Material Science and Technology Division, CSIR, NIST, Trivandrum. Dr. Vishwanath Rao, our beloved Principal. Dr. Archana P. Das, HOD, and the convener of this program. And HODs, Deans, Professors. This is a wonderful time. When I was sitting here, I was thinking, such a wonderful person, a scientist like him, today morning with us. And it was a knowledge erosion that happened for a few minutes. But it is really, I really appreciate and congratulate Dr. Archana P. Das to invite such a great personality for inaugurating this 5 days FDP program. So also I extend my sincere felicitations to all the experts, those who are engaged with the classes for 5 days, and also the participants from different walks of life, and all those who are involved in this, especially Dr. Ranjini and Dr. Preeti. They are the coordinators, and all the members of S&H. I extend my sincere felicitations. Thank you. All the best.
I request our director to hand over the memento to our chief guest. As we near to the end of this inaugural ceremony, it is time to express our gratitude to all those who have made this event possible. I invite Dr. Preeti PC to deliver the vote of thanks.
Respected Chief Guest, Dr. TPD Rajan Sir, our beloved Principal, Dr. Vishwanath Rao Sir, our Director, Reverend Father John Varghese Sir, our HOD, Archana P. Das Miss, all the faculties, deans, HODs, and all the family members of MBCT. A warm good morning to all. On behalf of Department of Science and Humanities, I stand here before today to express our sincere gratitude to everyone for making this inauguration ceremony a resounding success. First of all, we are extremely grateful to the today's esteemed guest of honor, Dr. TPD Rajan Sir, for taking the time out of his busy schedule to join us today and gives the importance of material science on science and technology. Next, thank you, sir. Next, we would like to express our sincere gratitude to our director, Reverend Father John Varghese Sir. Sir, your presence and blessings enlightened this program. Thank you, sir. We are also grateful to our principal, Dr. Vishwanath Rao Sir, for gracing this occasion with your presence and insightful words. Thank you, sir. A big thanks to our dear HOD, Archana P. Das Miss. Miss, your guidance, motivation, and advice gave the energy to organize this program. Thank you, Miss. A special word of thank you to all the deans, HODs, and the faculties of all the MBCT departments for joining us today. All of your presence has made this event a great success. Even a single thank you is not enough to express our sincere gratitude to the entire faculties of Science and Humanities for their dedication and commitment for the smooth running of this program. Thank you all. We would like to express our sincere gratitude to ITMS team for their technical support. And next, we are expressing our sincere gratitude to our housekeeping staffs for the venue arrangement. Thank you once again to everyone for making this inaugural function a great success. Thank you. Have a nice day.
Thank you, Miss. With that, we conclude the inaugural ceremony of our faculty development program. We look forward to an enriching journey ahead filled with learning and growth. Thank you once again to our esteemed guests, faculty members, non-teaching staffs, and all attendees for gracing this occasion with your presence. Have a wonderful day ahead. Refreshments are arranged outside the hall. We may now request everyone to have the refreshments.